Hi, it's Mr. Anderson, and this is Chemistry Essentials video 21. It's on metallic bonding. And it's important that you understand that you can't have one metallic bond. You have to have a number of atoms together sharing their electrons and therefore sharing their bonding. And so the way we look at metallic bonding is the electron sea model, where you have all of these electrons and they're shared by all the atoms. It creates a sea of electrons, and then the protons are kind of held on the inside of that. And so in metallic bonding, what we have are delocalized electrons, or electrons that have a freedom to move. And the way we visualize that is through this electron sea model. It accounts for a lot of the properties of metals, like their conductivity, malleability, ductility, low volatility. And sometimes we have to go to the shell model, however, to explain new phenomenon, and we'll get to that when we're looking at melting point. And all of that has to do with bonding. And so if we look at metallic bonding, or these shared bonds between all the metals, visualize it like this. We have the positive charges of the protons in the nucleus, and then we have electrons that are free to go. But they don't want to get too close to each other. They're going to repel each other. And so what they do is they simply drift around, and they're constantly in motion. And what you create is this sea of electrons that have a negative charge, and then the protons are going to be held on the inside of that. And that's the best way to visualize the metallic bonding. And remember, these are going to be transition metals. So these are going to be atoms that have a lot of unpaired electrons in their d orbital, and as a result, these electrons have a freedom to move. And as a result, we have all of these properties that come from metals. So number one, they're very good at conductivity. So that means conducting electricity and also conducting heat. And the reason why is that electricity, for example, is simply the flow of electrons. And so if we have free electrons, it's easy for them to flow through that metal. Likewise with heat, since those electrons and those atoms have a huge amount of freedom, we can move a lot of that energy through the material. They also are incredibly malleable, and what malleable means is that you can hit them and they're going to flatten out. And so if you're a blacksmith, you're using that property of heating up these atoms in the metallic bonds, and then as you hit it, you're able to slide them past one another. It's going to be smooth sliding. And that explains how we could get something like gold leaf, which is simply gold that we hit over and over and over again until it's razor thin. They also show ductility, and what ductility means is it's ductile, or that means that if we pull it, it's going to stretch rather than break. And so if we were to test the tensile strength of different materials, so what you do is you put them in a big vise like this, and then you simply pull on it. If something's ductile, what that means is as you pull on it, it's going to stretch out before it eventually breaks. If it's not, it's brittle, what it's going to do is simply break in half. And metals show this, and the reason they show that is that all of these atoms have freedom to move around each other. And so when you pull on it, it's going to stretch it out. They also show low volatility. What that means is that they're going to have a high melting point and a high boiling point. Why is that? Well, think of all the positive charges we have down in these metals. We have all these negative charges, and so there's going to be a huge attraction between the two. And so it's hard to pull off individual ones to make them a liquid or eventually to make them a gas. And so you would think as we move across the transition metals, so let's say we're going across this period from scandium to zinc, as we move across, we should be increasing the number of electrons, and so we should be increasing something like this, melting point. And it's not really right, and so let's look at what the data looks like. So as we move across the period, it starts to go up for a while, but then it dips, and then it eventually goes down quite a bit. And so this whole idea of an electron sea model works well, but when you get to something like this, we have to start digging into the shell model to make sense of it. And so let's start by looking at some electron configurations. So if we're looking at scandium, it's going to have 2 electrons in its 4s, and that's something interesting about transition metals. Their valence electrons are actually going to be at a higher level, but inside the s subshell. Anyway, as we move across, what we're doing is we're increasing the number of electrons. So we're increasing the number of valence electrons. And so as we go to titanium, and then as we go to vanadium, this all makes sense. If you can increase more of these electrons, increase more of that charge, it's going to be harder to get this thing to melt. But if you look here, when we get to chromium, it kind of dips. And the reason why is that it actually is not going to fill this 4s before it jumps into the 3d. And then as we go to magnesium, you get a real stable shell structure where all of these are filled, and so the melting point is going to drop off. But now that pattern picks up again. Okay, now we're going to start adding electrons. So when we go to iron and to cobalt and to nickel, Now we're adding these paired electrons, and as we pair those electrons, now we don't have those free electrons anymore, and so we're going to decrease the melting point as we get all the way down to zinc. And remember, as we get to zinc, we're moving over towards those nonmetals, and so we're starting to see odd properties here as well. And so metallic bonding is pretty simple. Did you learn to use a delocalized electron model to predict macroscopic properties of metals? If you understand the C model and you see how it affects conductivity, malleability, ductility, and low volatility, then you got it. And I hope that was helpful.